Trigonometry and complex numbers are two fields of mathematics that at first glance seem quite unrelated. One is an extension of the number system into bizarre imaginary territory, and the other is firmly focused on real lengths and angles. But there is one kind of major link between the two, a certain niche formula that you may or may not have seen before, and it's of course Euler's identity. E to the I theta equals cosine theta plus I sine theta. But that's not what this video is about, because it has been done to death. Hell, even I've made a video about Taylor series, which are key to proving this fact. Instead, what we're going to be talking about is something called de Moivre's theorem, which links complex numbers and trig together even more closely, and is actually quite useful. De Moivre's theorem is this here: cosine theta plus I sine theta, all to the power of n, equals cosine n theta plus I sine n theta. And it's really easy to prove this using Euler's identity. The identity tells us that the left-hand side here is e to the I theta to the n, and the right-hand side is e to the I n theta, and by our basic exponent laws, these are the same thing. So where is this useful? Well, the first immediate use of it is in calculating powers of complex numbers. Imagine you were tasked with calculating 9 plus 3 root 3i to the power of 13. Now if you were foolish enough to attempt to do this with a binomial expansion, it would take you a little bit, just a little bit of time to work it out. But if we convert this into modulus argument form, so we write it in terms of its distance from the origin and the angle it makes with the real axis, we instead get 6 root 3 cosine pi over 6 plus I sine pi over 6 all to the power of 13, which we can split up into the modulus and the argument bit to get this, and then applying de Moivre's theorem and dealing with the number at the front, we get 9,521,245,937,664 root 3 times cosine 13 pi over 6 plus I sine 13 pi over 6. And then we turn those trigonometric expressions back into numbers to arrive at our final answer of 14,288,868,906,496 plus 4,760,622,968,832 root 3 I. Now I promise you it would have taken a lot longer and a lot more effort to get to that answer if we hadn't used de Moivre's theorem. But this isn't the only place where it's useful. No, it can be used to generate trigonometric identities, specifically ones involving compound angles. Some of you might already be familiar with the compound angle formulae and double angle formulae for sine and cosine. They're on screen here in case you've never seen them before. Now these are cool and all, but once we have something like cosine 5 theta, they become less and less practical. I mean, let's take cosine 5 theta as an example. So cosine 5 theta equals cosine theta plus 4 theta, which is cosine theta cosine 4 theta minus sine theta sine 4 theta, which is equal to cosine theta cosine 2 theta plus 2 theta minus sine theta sine 2 theta plus 2 theta, and then it just reaches the point where I can genuinely write this out quicker than I could say it. Okay, so with all of that, we've reduced it to an expression only in terms of our cosine and sine theta and its powers. But I mean, this will be a pain to neaten up, and will be even more of a pain to write just in terms of cosines. So instead we fall back to de Moivre and consider this here. Cosine 5 theta plus I sine 5 theta equals cosine theta plus I sine theta all to the power of 5, which we can expand out like here just using the standard binomial expansion. And then what we do is we just equate the real parts of both sides, and we get cosine 5 theta equals cosine to the 5 theta minus 10 cosine cubed theta sine squared theta plus 5 cosine theta sine to the 4 theta. And that's it, already. It took a whopping 3 lines to get a pretty clean looking formula, and to be honest, it's not that much effort to get this all in terms of powers of just cosine. We can just spam the identity that sine squared theta equals 1 minus cosine squared theta until we reach this wonderful result right here. 16 cosine to the 5 theta minus 20 cosine cubed theta plus 5 cosine theta. And it's a really epic result. It's got nice numbers, it's got that plus minus plus pattern, kind of like the start of the Taylor series for sine, and I know it's an absurd thing to say, but it is very aesthetically pleasing. It's a very elegant result. It's also a lot easier to scale up than the other method. The only thing that really gets more complicated is turning it back into an expression in terms of a single trigonometric function, because you have to deal with bigger and bigger binomial expansions. But despite all of that, it's just not really useful. It's cool to be able to write things in terms of powers of just f of theta with no coefficient in front, but it actually makes life harder, because you're taking a single linear transformation of a function and turning it into the sum of multiple different non-linear transformations. So in a peculiar turn of events, what we'd rather have is the inverse of this, a way of turning powers of sine and cosine into these compound angle expressions. And to get there, we have to go back to Euler and redefine our fundamental trigonometric functions. So we know that e to the I theta is cosine theta plus I sine theta, and e to the I n theta equals cosine n theta plus I sine n theta. But what happens when we plug in minus theta? Believe it or not, we get cosine of minus theta plus I sine of minus theta. However, we can actually clean this up a little if we consider the nature of cosine and sine. If you take a look at a cosine curve, you'll see that cosine of minus theta is just equal to cosine of theta. The mathematical way of explaining this is saying that cosine is an even function. And if we do the same thing with sine, we see that sine of minus theta is equal to minus sine of theta, which means that sine is an odd function. And what that lets us do is simplify this down to cosine theta minus I sine theta. Then what we can do is add this to the original identity, and we get that e to the I theta plus e to the minus I theta equals 2 cosine theta. Or in other words, cosine theta equals e to the I theta plus e to the minus I theta all over 2. If you rinse and repeat this but subtract the two expressions from each other instead of adding them, you'll get that sine theta equals e to the I theta minus e to the minus I theta all over 2. Now something I really want to emphasize is that these are not definitions of sine and cosine, right? They're just identities, they're just rearrangements of what we already know that happen to have cosine or sine theta on the left hand side. Nevertheless, I think it is interesting to consider what it actually looks like when you plug a value of theta in. So let's start simple. Let's go for cosine of 30 degrees, or since we're working in radians, pi over 6. Let's start with our leftmost term here, e to the I pi over 6, which looks like a unit vector angled 30 degrees above the real axis. Then e to the minus I pi over 6 is that same unit vector, instead angled 30 degrees below the real axis. And adding these two together looks like putting them tip to tail. And immediately you can see just on this Argand diagram that our arrows are pointing to our real output. And as our value of theta goes up and up and up and up, this output changes as the exponential terms move in sync like some funky kind of double pendulum. But let's get back on track. And use this new knowledge to express powers of trig functions as sums of compound angles. We're going to be ambitious, we'll try cosine to the 7 of theta, which is a half e to the I theta plus e to the minus I theta, all to the power of 7. Now if we let z equal e to the I theta, then that means that this here is a half z plus 1 over z, all to the power of 7. Which we can split up into our two separate terms like so, and then binomially expanding this whole mess, we can get it onto this, before collecting terms like so to get this right here. And you might be thinking, cool, I know one term here, the very last one, it's 2 cosine theta. But we know more than that, because what is z to the 7? Well, z to the 7 is e to the I theta to the 7, which is e to the I 7 theta. So this expression here is actually just e to the I 7 theta plus e to the minus I 7 theta, which is 2 cosine 7 theta. And similarly, this next term is 2 cosine 5 theta, and the next 2 cosine 3 theta, and just like magic, we've turned our cosine to the power of 7 theta into 1 over 64 cosine 7 theta plus 7 cosine 5 theta plus 21 cosine 3 theta plus 35 cosine theta. We've gotten rid of all of the powers. And this can be kind of useful if you're trying to do integration, and for some reason you know about complex numbers but not basic substitution methods. Yeah. To be honest, neither of these two tricks I've shown off today are anything revolutionary, but it does show how interconnected the different parts of maths are and sheds a little light on how complex numbers are actually used, because they are a lot more rich and complex than just being the solutions to weird polynomials that would scare 15th century mathematicians. But anyway, let me know in the comments below if there are any other cool links I missed, and thanks for watching.